Okay, 2414, 9.7 notes, page 1 and 2. Let's talk about Taylor polynomials. So oftentimes some of the functions we want to know the values for, we don't know them off the top of our head, like the sine of 37 degrees or the sine of pi over 132 radians. We don't actually know the values. So someone came up with the idea that, well, if we know the values at a place close to that, we should be able to approximate the value. How do they do that? Well, let's think about a line. A line has a point and a slope. A quadratic has a point and a constantly changing slope. But we know how to find the slope at that point for a quadratic. That's the derivative and plugging in the x value. And the tangent line has a very close value to the actual function nearby that point. So the idea is we can use that to kind of create an approximation of the value. Now, how do you do that? You need the value of the function to match and the value at the derivative to match, and we'll create polynomials that can help us match things. It's maybe easier to see this in action than to talk about it. You can read more about Taylor polynomials online and how they came to be. Try to approximate, this is what it's asking, approximate f of x equals e to the x with a linear function at x equals 0. Now, of course, what do we know about e to the 0th power? It's 1. Okay, so we know f of 0, e to the 0, is 1. Now, what is f prime of, what's the derivative of e to the x? It's e to the x. So what's f prime of 0? It's still e to the 0th, which is 1. So these will give us, this is the constant that we need for our polynomial, and this is the derivative of the linear term. Because we took the derivative of e to the x, so we have to take the derivative of the linear approximating it as well. So what type of function has a constant when you take the derivative of it? Just regular x, especially if it's just 1. The derivative of x is 1. So this should give us the function y equals x plus 1 as an approximation for e to the x around 0. And when we think about the graph itself of e to the x, it does something like this. So very close to 0, it does seem like the line x plus 1 would be a good approximation, but obviously you can see as you go further away, the approximation becomes less and less valuable. So these are really only used to approximate as you get close to a point. For example, if I wanted to know what cosine of 0.1 is, I could use an approximation to do that. The interesting part about this is, do you ever wonder how your calculators know how the values of all those things? You think there's a table in your calculator that they look up and they can give you all the answers to what the sine of pi over 327 is? No, they program the functions for the Taylor polynomials, which we'll get to later, like a full, not just linear. They program them so the calculator can just plug in the number you want and spit out the value. One function, your calculator can handle it. Now, there are ways to make this more accurate than this picture is. Every time you go one derivative further, you control more and more. Of course, in order to go one derivative further, there'd have to be an x squared term, then an x cubed term, so on and so forth. So the polynomials just get longer and longer the more accurate you want to become. Because it's a little bit easier to approximate this curve, the more options you have. So let's look at page 2. Now, instead of approximating e to the x, we want to find the third degree Taylor polynomial. And that other one was the first degree because it was linear. Third degree will have 4 terms of the same thing, e to the x at x equals 0. So instead of just the first and the first, or plugging into the original and the first derivative, we have to go all the way down to the second and the third derivative. Now this is nice for us though, because what's all of the derivatives of e to the x? Still just e to the x, so these are all e to the 0. These are all e to the 0 power. They're all 1. So what does that mean? We know this produced the term 1 for our constant. This produced the term x, because the derivative of x, first derivative of x, is 1. Now I need something for whom the second derivative of x is 1. Now here's the problem. X squared's first derivative is 2x, and the second derivative is 2. It gets us close, but not quite. So what do I really need in front of this x squared? A 1/2. So 1/2 x squared gives us the second derivative of 1. Similarly, for x cubed, the third derivative is actually 6. So I need 1/6 x cubed to get this. So the Taylor polynomial approximation around e to the x, that's third degree, instead of just x plus 1, is now 1/6 x cubed plus 1/2 x squared plus x plus 1. Now, how does this help? Well, if we were, e is some value around near 2.7. If we were to just plug in 1 here, e to the first power, we would approximate e to the first power would be 2, which is kind of close, but not perfect. However, if we plug in 1 here, we get about 2.67. So already it's much closer, even for a value 1 away from where we're centering it, by getting just to the third degree Taylor polynomial, and we can go further than that if we want to. So that's why they're helpful. So you just got to get comfortable with doing this. Under this problem, there's an explanation of how to do things centered at numbers besides 0. Technically, if it's centered at 0, it's considered a Maclaurin polynomial. If it's centered anywhere else, it's a Taylor polynomial. The really Maclaurin polynomials are just a special case of Taylor polynomials. That's all we've done here. In the next video, we will look at how to find the Taylor polynomials for other things that maybe aren't centered at 1 and use them to make approximations.